Okay, so the first few sections, chapter 5, videos have been sort of lengthy, but this one is short, quick, to the point, and just want to run this section by called Speed of Rotation. Okay, so Wilde tells us when a DC motor is driving a load between no load and full load, that the IR drop, that portion of the equation that we account for the heat losses, the current times resistance drop that occurs in that armature circuit that's due to the armature resistance. When it gets to full load, that drop compared to the supply voltage is E sub S is really small. So at that point, what we can really say is that the armature voltage, the E sub O, is practically equal to the source voltage. Okay, so if we make that assumption, and it's a valid assumption to make, it allows us to do something else without going through a lot of complex math to get there, that would sort of go down this path. Okay, so what he says, and this is on page 100, what he says that is, if we're saying that E sub O is almost equal to E sub S, and we have this equation very often utilized, 4:1, what if we replaced E sub O with E sub S? Because again, what we're saying is, you know, they're almost equal at that point, you know, when we get to full load. And then if we have that, we make that assumption first, right? Assume this. Then he goes to create equation 5.7 that says that the speed, this is just this equation solved for n, says that the speed is equal to 60 times E sub S divided by Z, the number of conductors, times the flux per pole. And we're going to call that equation 5.7. And the E is the N is speed of rotation in RPMs. Of course, this is voltage, E sub S, total number of conductors. And what it shows, we can look at that equation and we can see that the speed is directly proportional to the supply voltage and inversely proportional to the flux per pole. Now, this is going to come in very useful soon, and we'll see that as we go forward. And one other quick thing I want to mention. What would you think would happen as this flux per pole were to get very, very small? Well, we would know that the relationship, you know, in this total thing, if this number is getting really small, then this speed is going to increase. And we're going to see that as a characteristic of a DC motor and something that we have to avoid to make sure that it doesn't get too small, or we can result in something called a runaway condition.